All right, IBAASL2. Today we're going to talk a little bit more about integrals, but now we're not going to do just sort of a general integral. We're going to talk about something called a definite integral. A definite integral has a lot of the same notation, but there's this sort of start and stop points on it. So like you start here, and you stop here. I'm going to teach you guys what this means and how to do it, and what it represents. It's a definite integral. Whenever you take a definite integral, it's going to be equal to just a number. Now, this is different than all the integral work that we've done so far, because usually when we integrate something, we get a function, something with x in it. But this will just be numbers when you evaluate a definite integral. The way you read that is an integral from a to b of f with respect to x. Before I show you guys how to do those, we're going to find the area of these shaded regions on these graphs. So on this first one here, on A, notice there's a horizontal line, and that is the function, f of x equals 4. We're going to find all the area that's underneath the function down to the x-axis. So that is a rectangle, and then if you count up blocks, I believe 1, 2, 3, 4, 5, that we have an area or a side of 5 here, and then a side of 4 here. So the area of this guy would be 20, length times width. This next one is a triangle, so let's do 1/2 base times height. So the base is 1, 2, 3. So this is a 3, and this is a 6. So when we do area equals 1/2 6 times 3, I believe this is 9. Here we have a trapezoid, and the trick, if you forgot how to find the area of a trapezoid, is that the area is 1/2, I forget how to write this, it's like B1 plus B2 all over H. It's like base 1, base 2. So here's base 1, here's base 2, here's your height. It's like on its side. Oh, wait, is that the way that they want us to do that one? You know what's tripping me out about this one is that I thought that this point right here landed on a nice whole number, but it doesn't. I mean, maybe we could use the slope. It goes down 1 over 2. So it goes down 1 over 2. So this would be like down 1/2 over 1. So it is a 1/2. Okay, using the slope, this would be 2.5. So this side is 2.5. And then this intersection, I think, is perfectly on 1. Let's see, down 1 over 2, down 1 over 2. Yeah, this one does land on 1. So this is a distance of 1. And then from 1 to 4, this is a different distance of 3. So the area equals 1/2. Whoa. Stop. Please come back. Get out of here. Oh my gosh. Oh, this is going terribly. Please just... Okay, yeah. There we go. Okay. 1/2. Can I, please? Oh my gosh, you guys. I should never have worked with an image so big. Okay. Oh, thank goodness. Okay. 1 base was 2.5. Then it was plus 1. And the height was 3. Oh, wait, I think I'm messing up the original equation. Then it's 1/2 base 1 plus base 2 times height. There it is. So 1/2, 2.5 plus 1 times a height of 3. So grab a calculator for that one for sure. This is 11. That's the height of that trapezoid. Now this guy is a circle with a radius of 4, but a full circle would be pi r squared. So we are going to do 1/2 pi r squared. So r squared is 4, so this is 16. So area equals 1/2 16 pi, which is 8 pi. I'm curious about what 8 pi is as a decimal, because I think it might come up that this is going to be 25.13. Now, you might be looking at these and being like, why on earth are we finding the area of all these things? Well, notice the theme each time is that there's some sort of equation. Like here it's negative 2x plus 4. Here it's negative 1/2 x plus 3. Here they give us the equation of the circle, which is square root 16 minus x squared. And each time we're finding the area underneath the curve or line down to the x-axis. What on earth does this have to do with integrals? Well, that's this part. So, notice on this first problem that the start and stop points, like we start at negative 3 and we go to the 2, and it's underneath this line, which is 4. If we zoom in here, this goes from negative 3 to 2, and the function is 4. On the next one, if you look at the start and stop points of the x-axis, it starts at negative 1, stops at 2, and here's the function. Starts at negative 1, stops at 2, here's the function. So each of these are the left bound, right bound, and then the thing that's in the parentheses that you're integrating is the actual function. So like, for instance, with the circle one, it goes from negative 4 to positive 4, which is negative 4, positive 4. And then the curve is square root of 16 minus x squared. Now, if I just ask you to find these integrals, you guys don't exactly know how to do yet. I think if I took the starts and stops away, you could do A, B, and C, but you can't really do D, because it's like a chain rule where the inside function isn't present, and we don't know how to do that. So I'm going to teach you guys a method to be able to do these definite integrals on a graphing calculator. So on a calculator, you're going to hit the math button, then arrow down to number 9, which is FNINT parentheses. Now, if you're on an 84 or 84 plus or something like that, and you hit that, you're going to get a nice menu that looks like this. It's going to be a little integral symbol. There's going to be a box here, and then parentheses, and a box here, parentheses, and then a D box. So you can actually fill in these spots with the information from the problem that you're trying to do. Now, if you're on an 83, you're just going to get something like this. It's just going to say, what does it say? DFNINT. So it's just going to put it on your home screen. And the way you do this is you put f of x first, then the variable you're taking respect to, so it's usually x, and then it's going to be the start number and the stop number. So it doesn't go quite in order. Like you'd think it would start with the start and stop, and then it'd be the function, and then differentiate with respect to x, but it doesn't go in that order. So if you hit that on your calculator for A, and you punch those things in, negative 3 to 2 of 4 dx is 20. If I go back up here, look, the area was 20. If you differentiate part B and plug it all into the calculator, I believe part B is 9. Part C, if you plug it into your calculator, which you guys should definitely try this right now on your own. Grab a calculator, plug some of these in, and see what they equal. C, we should get 11, if I did my math right, and D, you should get 25.13. Here, I'll do D, just to make sure we're on the same page. Whoa. Math, and then it's going to go from negative 4 up to positive 4, and then I'm going to put the square root of 16 minus x squared would differentiate with respect to x. Well, it's thinking for a long time. Must be a hard integral. Yep, 25.13. We nailed it. So if you integrate a function from a certain start to a stop point, you're finding the area underneath the curve. Now consider this shaded region on the diagram. Write down the definite integral that gives you the area of the shaded region and evaluate it using your GDC. Well, the problem with this, there's two different ways you can do it. You could do it in pieces by saying you can find the equation of this line and then the equation of this line and then add them together. Or you could recognize that this is an upside down absolute value. So when f of x is equal to absolute value of x, the graph of it looks like this. It comes down at a negative slope, it bounces off the origin, and goes up at a positive slope of 1. So this is an upside down absolute value that's been shifted up by 3 because the vertex, if you want to call it that, is normally on the origin, but now the vertex is up on the 3. So it's been flipped upside down and moved up 3. The start point is negative 3 and the stop point is 3. So we know when we integrate, it's going to be negative 3 to positive 3. Then the function that we're integrating is an upside down absolute value that's been shifted 3 up. If you punch that into your GDC, which right now I'm fine with you guys using that unless it says to not use a GDC, is 9. Now, is that true if you just find the area of this triangle? Like base would be 6, height would be 3. If you do 1/2 base times height, would you get 9? Is it really 6? Yes. Did I do that right? So yeah, you can always check to make sure the area does add up to what you're trying to get. Oh, sorry, the base is 6. Yeah, so 1/2 6 times 3, it is 9. It works. Find the area using a geometric method. Oh, I was basically just doing what they asked us to do. I didn't read ahead. I was already checking my work. Yeah, you guys, the base of this triangle is 6 and the height is 3. So the area of the triangle is going to be 1/2 base times height, which is 9. So it works. Now, you guys, if you go to integrate this, like if you, in your calculator, if you were trying to find the area of those two shaded regions, then you would just do negative 3 to positive 3, x plus 1, dx. Now, when you do that, here, let's figure out what it actually is. I'm grabbing my calculator. I'm using fn int. I'm going negative 3, positive 3, x plus 1, dx. This is equal to 6. Now, if I look at just their areas here, like if we just figure out what the area of each of these are, they're both triangles, so we can use 1/2 base times height. So this distance is 4. This distance is also 4. So if I do 1/2 base times height for this top part, which is 8. So the area of this top part is 8. If I look at the area of this guy, the height is 2 and the base is also 2. So area would be 1/2 2 times 2, which is 2. So the area of this triangle is 2 and the area of this one is 8. 8 plus 2 is 10, not 6. So you guys, how do you think that they got 6 over here? Can you see the relation between these two numbers of 8 and 2, how you would make a 6? That's right, you guys. 8 minus 2 is equal to 6. So what's happening here is anytime we're above the x-axis, these are positive areas. Below the x-axis, negative areas, which I realize that's weird to think, oh, well, you can't have a negative area, Jolly, but in terms of calculus, you can. So this part here would be a -2 area, and then this part would be a +8. So when you add -8 and +2, when you integrate the whole thing, you get 6. This is just another way of kind of summating what we just said, where if you're, take an integral from a to b of this function x, you're going to find the purple area under the curve. It represents area. Now, this one, they don't really give us the equation, so we can't really use our calculator. But what we can do is evaluate 0 to 12 of f of x dx using our area methods. So what we're going to have to do is evaluate in these chunks, that we're going to have to do this triangle, then subtract, I'll use a different color, this trapezoid, and then we're going to have to add whatever this triangle is. So first piece, the base is 5, the height is 4. So area equals 1/2 5 times 4, which is 10. This part, which is going to be negative, is a trapezoid where the base is 5, and then from 6 to 8 is 2. So this is 5, this is 2. It's got a height of 4. So the area of that one is 1/2 5 plus 2 times 4, which is 14. But remember, this will be a negative area because it's below the x-axis. Then this triangle has got a base of 2, a height of 4. So the area of this guy is 1/2 2 times 4, which is 4. This means that 0 to 12 f of x dx is going to be equal to 10 plus -14 plus 4, which equals 0. That means that the orange areas are the exact same area as the red one, the trapezoid. And they cancel each other out, the 2 positives and the 1 negative. Last thing, I apologize, I'm running short on time. They give us these definite integrals. 0 to 3, 3 to 4, those are both for f, then 0 to 3 for g, and 0 to 6 for g. We're going to use those to figure out these problems down here. So this first one, part A. This 2 on the outside can be brought out, and the fact that there's 2 functions being added means that we can rewrite it like this. 2, 0 to 3, f of x plus, oh, I forgot my dx. dx plus 0 to 3, g of x dx. Now, those pieces we already have up here, like 0 to 3 for f of x is 5, and then 0 to 3 for g of x is -6. So this can be rewritten as 2 times 5 plus -6, which is 4. So part A is 4. Part B, 0 to 4 of f of x. Well, 0 to 4, we don't really have a 0 to 4, but if you look up here, we have a 0 to 3 and then a 3 to 4. So you can just add those two things together. So 0 to 4 f of x dx is equal to 0 to 3 f of x dx plus 3 to 4 f of x dx. So this is 5 plus 2, which is 7. Part C, we're going 3 to 3 on g of x. Okay, so first of all, that's like a trick question, the 3 to 3 g of x dx. If you're going from 3 and stopping at 3, you're not really getting any area because, yeah, there's nothing. When you start at 3 and stop at 3, there's no area involved. The second part is interesting that these two things are flipped. Really, the trick with that one, since we already have 3 to 4 for f up here, if you're going backwards when they're flipped, it's just going to be a negative version of that. So this is going to be 0 plus -2, which is -2. Part D. 3 to 6 on G. Well, what are we working with here? Well, they give us 0 to 6, but we only want 3 to 6, so we're going to have to subtract out the 0 to 3. So this means 3 to 6 g of x dx is going to be equal to 0 to 6 g of x dx minus 0 to 3 g of x dx. So when you subtract those out, what are they? 10 and then minus a -6. So I believe that is 16. All right, you guys, I'm going to let you try the last one, but I'll let you know that the answer to the last one should be 30. You're just going 2 to 8. Like this 3 can come out front. And then if you're going from 2 to 8 on G. Oh, this one's kind of tricky. This is a horizontal shift from transformations. So it doesn't actually change the area. So you can actually take 0 to 6 instead of 2 to 8 because this is a distance of 6 on the x-axis. Come see me in class if you want to see how to do that one. All right, guys. Good luck.